Hello my friends, here's the description on the Raspberry Pi arcade hat that I've shown in a previous upcoming projects video. As you can see here, this connection to the Pi, we've got rows and columns listed and also ones labeled as can't use. Now that can't use means that those are the lines used by the Hi-Fi barrier hat for the sound. Now this is based on if you're using a Hi-Fi barrier amp 2 for your audio. You could use the other audio, but that would require an external amplifier to run the speakers. So I went with amp 2 because it's a nice neat stack. So as you can see, it's this basic row and column keyboard input matrix across basically 10 GPIO, because what's not shown here is column 9 for the credit input, which is controlled via these transistors on this side here. We have 3 major connections here, which are basically the bypassing of the coin pull or the counter, the actual coin counter itself, and then the connection for the credit input. So in this case, where it's coming from a coin input, note acceptor, or a credit card facility, because this board is designed for use in revenue service. If the hat's going to be used in what I call free play mode, you would still leave the counter bypass enabled, so there's a jump between MEC 5 volts not and count pulse, and there'll be a jump between no credit and plus 5 volts. So every time you press a button on the credit input from the debounce credit buttons here, primarily player 1, that would send credits into the machine in a free play situation. If it was a 4-player game, then obviously you'd press it for each individual player. So over here with this part of the control circuitry, we've got a couple of 555 timers, one functioning as a 1 MHz clock, the other functioning as a one-shot timer. Now the reason for the one-shot timer is that because I'm using digital electronics here instead of a microcontroller, what this does is it actually puts the counter into the correct mode. So when you're feeding credits in via this voltage converter to convert the 12 volt to a 5 volt signal, it's feeding credits in and the counter needs to count up. Now I'll show the counter shortly. And then we've got this simple transistor AND gate here, which basically makes sure that credit pulses only go through whilst the timer is in up count mode. Now it's actually delayed through this flip-flop to make sure that the counter has time to enable into up count mode and be allowed to settle. Because I'm using digital electronics here and basically nothing that actually has delays and stuff like that, I actually have to make sure I delay the pulses going to the counter so that it doesn't actually send through signals when the equipment is not, when the electronics are not ready to receive signals. Now obviously the pulses coming from the MECs are fairly large pulses, so they would be active going through while it's getting ready, but to prevent erroneous signals causing more credits going in than they need to be, basically I have the flip-flop there delaying the pulse signal going to the counter to allow the one-shot timer here to put the counter into up count mode. I also have an inverted signal here because for the other parts of the electronics, as in regards to the actual pulses that actually control the counter, need to be in an inverted signal, because the signal coming from the MECs and the parts and stuff that puts credits in has the signal line tied high and then it gets pulled to ground. That's great for triggering the 555 timer, and that's how most of them are designed. Whereas for the counter to work, it needs to be tied low and being pulled high when a credit comes in. So because the electronics works in that fashion, I have to invert the signal going to the counter, hence why you see here on the counter bypass the center pin's the inverted signal, not the non-inverted signal from the MEC. So here's the counter circuitry. So we've got a reset, a 555 timer again running in one-shot mode, this time not being re-triggered because there's no extra signal to re-trigger the timer. And what this does is that it basically puts the counters into reset upon startup to make sure they're in their default state of 0 credits loaded into the machine. And then through the interface, we've got the direction input, so whether it's in up or down count, Now count 0 is a signal going back to the board to say whether or not there are credits present, and then of course the MEC 5 volts counter board, which basically means that's the pulses or the clock signal, the credit pulses coming in to whether or not to add a credit to the counter or remove a credit. Now the count 0 signal is actually worked out through feeding these 4 lines and these 4 lines into a series of OR gates to basically find out whether or not, if any of these lines are actually high, it will cause count 0 to be high. And what that means is, it means that it's telling the board that there is a credit present that can be put through to the Raspberry Pi's currently emulated ROM. So basically they are connected via, they are held to ground unless they are pulled high, basically. So this resistor here is holding to ground, and in the event that they are pulled high, they will say it's to make sure that the outputs are not floating and causing erroneous inputs on the OR gates, causing count 0 to potentially be high. So over here we've got basic demount circuitry, including what I call blocking signals. So basically here, what's going on is that the button will hold the output to ground. So it will be connected normally closed, so that when you press the button, it removes the grounding and allows the output to be high. So this sends a high signal through to the AND gate. Now in doing so, when that signal goes through via the AND gates up here, it creates a number of different signals. So the first one that goes to, it creates the verified credit signal. So the moment, say, player 1 pushes their button, it will send a signal through to this transistor on the other 3 buttons, cutting off this transistor's connection. So the other players could try and press their buttons as much as they like. The input has been cut off, so it's actually a low signal at their input, so their credits will not go through until the player releases their button, which allows this transistor to go closed, so this transistor conducts again. So it's always conducting unless another button is being pressed. And of course this one, basically this AND gate here basically says if there is a credit pulse, which is actually generated by pressing the button. So when you press the button and it goes high, it will generate a credit pulse output through this series of OR gates. So basically these OR gates basically pretty much work out the whether there is a high. So it causes a credit pulse to go high. Player 1 verified credit is obviously going high due to this AND gate here, and it generates a credit pulse, which generates a credit out, and that credit out goes to these various transistors, which then cause their bases to conduct and obviously send a signal through to the Pi. And then down here is just the basic buck converter to convert the 24 volts in on the board into 12 volts to run the MECs. So in the next screen, I will go over the design of the PCB, and we'll go from there. Okay, so here with the PCB, as you can see how things are laid out, all the components are on the top side here, but the through-hole components are on the other side. Now, there's a reason why I've done this. So under here will be the Raspberry Pi. So the Hi-Fi barrier will be just underneath that. The Raspberry Pi underneath again. This is an access holder, access to screw terminals on the Hi-Fi berry. Connection for power, speakers, etc. You've got the various componentry here, input control, and of course the credit control. So the way this board is designed is that you can squeegee on all the solder paste you need, then place your components, put it either into a reflow oven or onto a heated plate, and it will heat it up and solder it on. So we'll go over to the 3D viewer. So here we are again looking at the top side. As you can see, all the components are on this side. Ignore this header here. That will basically have a header on the other side, because when I go and flip the board around in the 3D viewer, this is actually the way that it actually will sit in the arcade. So where this dashed holes are, that board snaps off, That's the counter board, which is designed to be mounted elsewhere so people can see the coins or credits that have been put into the machine. You've got our voltage connections here, so 24 volts in from a 24 volt supply with 12 volts out, obviously from the buck converter, and also then also having 24 volts out again for any additional stuff like lighting and stuff like that. So then the high berry hat goes there, and the Raspberry Pi on top accordingly, obviously upside down. And then you've got your screw connections here for like spare inputs, and then you've got your 4 players. Basically, 1 through 8 are the columns on the matrix, and the signal ground are the rows. So basically row 1, 2, 3, 4, and 5. And of course here are the credit input buttons, so that will be a normally closed wiring. That would be connected here. So they are separate to the input matrix because of the multiplex control. So that's pretty much the basic rundown of how the PCB will look. So once they turn up from JLCPCB, I'll do an assembly video, and then basically I'll also then do an assembly of the arcade as well, which I'm currently building. I've recorded some video for that, and that video will drop once I've got the arcade complete. So I'll see you then.